Yeah, I'm really excited to talk about Nix. These slides are actually from a talk I gave at Plow. It's been a little over a year now, actually. I've tried to update them a little bit, but might be a little bit of older stuff in there. But when I see it, I'll try to make a note of that. This talk sort of assumed a little bit of familiarity with what Nix was already. So before I dive into it, I'll just talk briefly about that. The basic idea behind Nix is that if you can build software in a fairly isolated environment, somebody made an analogy to a Docker container that I thought was fairly apt, where you control everything that the build process has access to, then you can not only ensure reproducibility of builds, but actually the builds are so reproducible that you can actually cache them across systems and just sort of look them up by a hash. And you can do dependency resolution using that same hash. So if anyone's used Nix and has seen the Nix store paths, which we'll see a little bit of in this presentation, where it says /nix/store and then a base 64 encoded hash and then some name, that hash is what's being used to actually look stuff up. So the neat thing is that means Nix is a reproducible build system and a package manager and a neat way of deploying software by copying these hashed paths over the network to systems that you're deploying to. Nix is also the name of the language that's used to sort of write down these build instructions and create these reproducible builds. Does anyone have any questions about that before we dive in and talk about how that happens? I know, give just a little bit of time so Scott has time to relay if there are questions.
Nothing so far.
Okay. All right, then we'll just dive in. So we'll talk about we'll run briefly through the Nix expression language first. It's a functional language. It's a lazy language, so it sounds like Haskell. But I've taken to describing it as the JavaScript of build description languages, because despite being lazy and functional, it's dynamically typed and has a lot of other very dynamic language features that make it not really feel like Haskell or any similar language at all. It starts off fairly simple. There's a really basic literal types with strings. There's a way to quote inline in a string. So if I have a string, this cabal install inside the curly braces is a variable, a string typed variable. And so in this string expression, that will get replaced with the string in the variable. You can write down a relative path, and that will get replaced by, that will get looked up relative to the path to the file, the Nix file that's being evaluated, and get replaced by the absolute path. And you can write down URLs as a literal without quotes. Lists look like Haskell lists, except they're space separated instead of comma separated. Another weird thing is that even though Nix is lazy, its lists are spine strict and value lazy. So I can't write down the famous Haskell fib function because the lists are spine strict. You have to evaluate the whole spine of the list with the pointers to each of the lazy elements. So I could have some lazy computation in each of these slots, but the whole structure of the list has to be evaluated all at once. The biggest, the most used kind of data structure in Nix, though, is called an attribute set, and it just looks like this. It's just a kind of like a record kind of like a hash set that has, or a JavaScript object that has names and values. And these values can be, Nix is dynamically typed, so these values can be polymorphic in the same attribute set, and often are. And you can freely combine attribute sets. They can be mutually recursive, though. So if you put this rec keyword in front, then every name you define in the attribute set is in scope for every value. So here I can write down developer is Edward.Amsden, and then I can use that string splice from before and put it in the email. Nix is a functional language. It has a lambda expression, which is just written as a single argument name colon an expression. So for multi-argument, you just write argument 1 colon argument 2 colon, and you wind up with a curried multi-argument lambda. You can pattern match on an attribute set from a lambda. If you write down 2 attribute names in your pattern separated by commas, or if you write down just attribute names separated by commas, it will insist that its argument be an attribute set with exactly those names, no other names, and not missing any of those names, and will evaluate to an error if that doesn't happen. You can allow other names by including an ellipsis, 3 periods after your list of attributes. And you can name the whole argument so that you can refer to the attribute set as a whole. This is exactly like the at pattern in Haskell. And you can provide default values so that your argument can omit some of the attributes. So you can combine this with the ellipsis and basically match any attribute set. So here we're saying we take an attribute set, looks like before with developer and email, but if I don't specify the developer, it defaults to Scott Murphy. And these patterns are recursively in scope for the default values, so I can refer to the developer argument in the default value for email. And then if I were to pass an attribute set with just developer equals Edward.Amsden, this default value would then be Edward Amsden at plowtech.net. Nix has let bindings that, again, are mostly like Haskell's let bindings in that they're actually let rec bindings. Or is that right? You have to say, I think, yeah, the let bindings are recursive by default. A couple of things that tend to confuse people because they read this as sort of object-oriented, but it's not really. There's a keyword called inherit that lets you pull something from your scope, from the variables that are in scope, and include them as attributes in your attribute set. So here, I've got two bindings in my let, a set and another set. But then within a set, I say, okay, I want an attribute called a set that I just want to have the value from the scope. So it's sort of recursively referring to this, which is fine because attribute sets are lazy, so they can sort of be recursive in that way. And another set, which is defined down here. So the dot syntax is just how you reference a attribute of an attribute set. So I can refer to another set as an attribute of a set and get this, and then also refer to a set as an attribute of another set. And then finally just pull X out of it. You can go the other way, and you can bring the values in an attribute set into scope. So if I say with a set dot another set dot a set, which is just a set because we have the same thing down here, this evaluates exactly the same way because all of the values from a set get brought into scope after the semicolon. So I could refer to X, name, a set, and another set, and I would get the values as specified in the attribute set. So this is something that you might have trouble with in a statically typed language, but Nix, being a dynamically typed language, lets you do. You can do string splices in attribute names. So you can take a parameter, which sets, remember the colon is just a lambda, and then you can refer to that variable as a splice in the name of the attribute you're selecting. So if I were to pass an empty string for which set, then this would select aset.aset.x. If I were to pass NOTHER into which set, then this would evaluate to another set, and I would get aset.anotherset.x. It's not something you use very often, but it is something that gets used occasionally. So one way to figure out the stuff with inherit and with is just to think of attribute sets as sort of packing up your current lexical scope or part of it. So inherit says you can select assignments from your current lexical scope, put them in an attribute set. And then with says, okay, give me an attribute set, and I'll take all of the assignments from that attribute set and put them into scope in the sub-expression that follows that semicolon. Okay, so that's the expression language. So now we'll talk about how we actually specify how software gets built inside of Nix. Any questions so far before we go on? That's sort of just introductory material so you can read the Nix code that follows.
No, I don't see any questions there.
Okay.
One thing that I think I have a question about is it seems like so URLs are actual literals in the language. Is that what I saw?
That's correct.
Okay, that's a little unusual.
It's very unusual, but it's essentially just a shortcut to save having to write quotes around your URLs.
I see.
There doesn't really have any use other than that. You can always pass a string where a URL is expected. So a derivation is something that describes to Nix how to build a particular artifact. It could be a piece of software, could just be a file, could be a archive, could be a Docker image, but it just builds, tells Nix how to build some artifact. As far as Nix is concerned, if you have an attribute set where you have an attribute type and that equals derivation, it will try to treat it as a derivation. In the Nix store, which is where all of the Nix artifacts actually wind up, it will be a file in the Nix store with a .drv extension. There's a command Nix instantiate where you pass it a Nix expression that evaluates to an attribute set like this with type equals derivation, and it will write that .drv file to the store. There's a low-level constructor in the Nix language. So there's just a built-in function called derivation that you almost never use because there's higher level wrappings around it. But that is that will take some arguments and build a derivation expression for you. The basic things you need for a derivation to be valid for Nix instantiate to actually write it to the store, it needs to have a name, it needs to have a builder, which is a script that will actually run for the build, and a system. So that system will be matched against the architecture to see if it can be built on the current system. And then the output will look something like this. again, you'll almost never actually wind up looking at this. If we pretty print that though, it will say here, when I'm done, I'm going to write what I built out to this place. And notice that even though we've just made the derivation, we haven't actually run this derivation yet. We have just specified how it's going to be built. We already know what hash it's going to have in the Nix store. And that's because the hash is a hash of essentially all the arguments and all of the dependencies. You notice there's input SRCs and input DRVs here. Those are things that that's empty for this because we didn't give it any, but those are things that it's going to that script is going to be able to refer to when it runs. Remember I said that the key insight of Nix is that if you can tightly control what the build has access to, that's what you need to do to make your builds repeatable. So this is where that actually gets specified. This is how it can actually have access to something. There's a couple different pretty printers you can look if you want to see, if you make a derivation and you want to just look at it and see how it came out without running it. The Nix command has a show derivation subcommand, and there's a package Nix derivation on Hackage, so you can install it with Cabal install, and then that will give you the pretty derivation command. I like Nix show derivation better. Pretty derivation is mostly just indenting stuff. It doesn't actually re-render it into something nicer than a term. All right, so when we actually work with Nix, we're usually going to work with something called a package set. So a package set is a set of derivations that we can use to a set of derivations that we can build. So it's an attribute set where each of the values are a derivation. So if I have a package set of just basic packages for Linux, I might have a .kernel attribute, I might have a .busybox attribute, a .grub attribute. The canonical set that everybody starts from is called Nixpkgs or Nixpkgs. This contains thousands and thousands of derivations. Just to give you, probably better to go in here, just to give you an idea of what the source for a package might look like. This is in Nixpkgs how you build the AMS, the also modular synthesizer application. So it says where to get the source from. It says what it needs present at build time. These are other attributes from Nixpkgs. So these are the things it needs available at build time. And you notice there's very little about how to build it. And that's because we're making a function called here standard n.mk derivation that has sort of build something with a default build script that basically looks at the source and looks for autoconf stuff, builds a make file, and then runs make on that make file. So you can get a hold of Nixpkgs in your Nix expression a couple of ways. If you have Nix installed, then there's some default checkout of Nixpkgs somewhere that you can get at through this import Nixpkgs expression. Or you can write a something like this where you get Nixpkgs at a particular revision from Git, or you can use niv. And niv is my preferred way of referencing external Nix code in my Nix builds. What niv does is it maintains a sources.json file that talks about all of the external Nix that we want. says what branch we're tracking, what current revision we have checked out, what the URL that we're checking it out from is. And then you can simply tell it to update and it will pick, it will get the latest revision from that Git branch. The neat thing is you can check in that sources.json file into your repository, and then everyone is using the exact same versions of the Nix code. And it just is that last little step to making your builds reproducible. So the convention when you're within Nix packages and when you're making other sets is that you write your packages as functions. So you write an exact pattern match with the attribute names for all the things you're going to depend on, both build dependencies and runtime dependencies. And you write the derivation call. So if we go back over here, you can see this part here. This is a lambda with all of the names. And there's a little bit of magic in Nix that lets you query about a function and ask what names it expects in its pattern, and then it will go look those up in an attribute set. So, so it looks like a lambda, and then the result is this call to MK derivation. So what is that standard environment? We'll talk about that in more detail. The standard environment describes the usual way that we are going to build packages. A really simple call to the standard environment if we're going to build libfoo just has to say what the name of the package is and where we get the source from. So Nix has these primitives that result in essentially further derivations that will go visit a URL and fetch the source. And then the way we make it reproducible is we specify what the hash should be. So either the source will have this SHA hash, or there will be an error. So obviously when you update the version of libfoo and you want to build libfoo 1.2.4, you have to also update this hash. And then, like I said before, it will generate a derivation that runs a standard builder script that will try to do autoconf and then make install into the path, the predetermined path in the Nix store. So this build script actually runs in several steps, and you can configure and override each of these steps to deal with software that doesn't build in exactly that standardized way. So the first thing it does is it unpacks the source. So it checks if the source that you're downloading is a tarball or a zip file or several other kinds of archive formats. It runs autoconf and then /configure on the source. You can override that to configure a different way. Runs make to build it. Again, you can override that. It runs make check to run any tests. And then it runs make install to copy the artifacts into the proper path in the Nix store. Finally, it will do some fix up because Nix tries to make sure that nothing has any dependencies outside the Nix store. So for instance, if your thing has a script that runs with bash, it wants it to get bash from that package set and not from your system. So it will look at around for hash bang lines and scripts and patch those up. It will try to patch up library paths so that those, instead of being relative, point to the Nix store, like shared object paths in binaries. So if libfoo has some dependencies that it needs present, we can specify those dependencies in our argument list here and then provide them as the build inputs argument. What that will do is any binaries that come from those packages will be available on the path in the build script. So now Perl will be in your path when the build script runs. So if your makefile references Perl to be able to run it. Headers are visible. So if you headers go in your include path and libraries go in your library path, so that your makefile knows where to find libraries from these build inputs. So like I said, packages are by convention functions. So those functions need those dependencies as arguments. So when we call a package, we produce an actual derivation by supplying those dependencies from the package set that we're calling from. So if we have Nixpkgs available in the packages variable, it will have an attribute called call package. We can pass the package that we want and any additional arguments that aren't going to be supplied from the attribute set. You can also, call package will sort of check the type, and if it's a function, it will just try to supply arguments to that function. You can also supply a file, which it will then load and then evaluate. So package sets are sets of derivations. Packages are functions from the derivations for their dependencies to derivations for the software that you're packaging. And call package produces the derivation for a package by supplying the dependencies from the set that you called it from. If you want to add packages to a set or modify or override existing packages, well, that's what the next section is about. So overlays are something that when people get into Nix and they say, okay, I want the current version of Nixpkgs, but I want libfoo 1.2.4 instead of 1.2.3, and I don't want to wait for that patch to land in Nixpkgs and then import the new Nixpkgs. So I want to use Nixpkgs with one additional package or a different version. And people are told to use overlays. It becomes kind of confusing, but overlays are just a lazy knot tying, if you're familiar with that from Haskell, on top of a package set. And they look like this. You fold the overlay over an overlay takes two arguments, self and super. Super means everything in the fold up to this point, and self means the whole fold. So every overlay in this fold has access to the whole package, and that excuse me, that's important so that if you want to talk about a package that you're not specifying in your current overlay, it doesn't matter whether your overlay comes before or after another overlay for which version of the package you get. So like I said, overlays are functions that take a self argument and a super argument. The first argument is the package set after all the overlays are applied. You use this for dependencies for any packages you're adding, for the standard environment, for call package. The second argument is the package set after all overlays before this one is applied. And this is where you get stuff that you're going to make changes to from. So if you're overriding a package, you don't want to write the whole thing from scratch. You just want to change maybe the version and the hash. You get it from super so that you don't introduce infinite recursion. If you're adding a package, you can write your package down and you want to add it to the package set, get its dependencies from that package set, use call package from the self argument. If you're specifying a dependency, note here that we want to override the VLC package and have it use make MKV to supply the lib Blu-ray library. Excuse me, because make MKV does lib Blu-ray emulation. So we're not getting VLC. We're setting what VLC is, so we're not going to get VLC from self, because then we would have an infinite recursion of overrides. But we are we're getting lib Blu-ray from self because we're not redefining lib Blu-ray. We're just saying that lib Blu-ray argument to VLC is different. So this dot override function just changes one or more of the arguments with which a package is called. Does anyone have any questions before I go on a little bit more?
See any, but that supercell stuff. So the VLC. So you're using the VLC that you're setting it equal to. You're calling the function that's already there, right? That override is already there as part of the
Right.
VLC
Yeah.
derivation.
So if you use MK derivation, then, or if you use call package to build, so here we said self.call package, my package, it will add to that derivation an override attribute, so that will give you that derivation again, but with the arguments changed.
So to me, this looks like the kind of thing that just isn't in a traditional package manager, right? Like, I don't know how to make Debian build all of a package the exact same, only switch one dependency.
Right. And this is one of the other innovations, is you have a composable way of building not just a package, but a set of packages, and then modifying a set of packages. And this is what basically everyone who uses Nix to build their own software does. They take Nix packages and they layer on overlays that talk about how to build their own things. So they get their dependencies for various open source things from Nix packages, or from various open source overlays to Nix packages, which is something we do at Plow for our Haskell stuff. We don't use the built-in Nix packages Haskell stuff. We use an open source overlay that has some nicer features. And for buckle script, we actually use a open source overlay to provide our buckle script infrastructure in Nix. So we can compose, everything from libc and GCC on up is coming out of Nix packages, so that the builds are exactly reproducible. And even the version of Bash that's being used to run the build script is coming out of Nix packages. But we can compose all of that, excuse me, so that we have the things we want to get from Nix packages come from Nix packages, and the things we want to specify exactly for ourselves, we can do that.
Yeah, it's really slick.
So since this is an introductory talk, I actually want to try to pull up a terminal real quick and show off just a little bit of what you can do with Nix. Something I don't have in these slides is something that is used when you're using Nix for sort of system package management. Like if you're using Nix OS, or even if you just want to get a few packages from Nix, if you're running on Ubuntu or something, Nix has another feature called environments that are managed with the Nix env command. So environments are basically just symlinks kept in a particular place that are symlinks to Nix path stores, and that are themselves sort of combinations of other Nix path stores. So if you have Nix set up and you've been using it, then in your home directory, you'll have a symlink called .nix profile that will point to actually another symlink that points to yet another symlink, because they're versioned and you can roll them back. That points to a path in the store. the neat thing about this is because all this stuff lives in the store and it's all been built isolated from other builds, I can roll back and now if I look at that, it says now it's profile 74. The last thing I did was actually to install ocular. So now if I say which ocular, it says there isn't one. Then I can switch back to profile I had before. And now I have ocular in my bin directory. So I have, every time I do an operation on my environment, I'm building another path in the Nix store, and I can, and because all of these symlinks are saved, just sort of numerically, I have generations of my user package set. Not only that, but because these are all installed in the Nix store and then assembled as a store just for me, I can have a different package set than another user on my system, and yet a different package set from the set of packages available to everyone on the system. So I actually have, I'm running NixOS, which means my whole system is managed in this way, and I could roll back my NixOS system in the same way. So if I look at what that is a symlink to, I'm on generation 11 of my system. And you can see I have a whole bunch of generations of my system that I could roll back to any one of these states of my system.
That's really slick, especially if you were wanting to like try out a new version of a package and then
Right.
roll back.
Right. Another thing that's neat is separately from that, without having to set up any kind of tool chain on my system beforehand, I actually pulled the slides for this talk. I was looking around and realized that I didn't have them on the latest install of my system. I had them in a backup. I didn't have to reinstall tech or anything like that. I just grabbed, this is all the stuff for this slide. And if I look at default.nix here, I'm going to blow this up a little bit so everyone can see. If I look at default.nix, actually, if I look at, we'll just look at it read only. I'll look at .nix. So if I look at this, you can see that I'm telling it here how I want it to build. I get text as a build input, and I actually said how I'm gonna, what exactly text is in that default.nix. But then I overrode the build phase. So instead of running make, it's using LaTeX MK, and the install phase, so it's just a copy command and not a make install command.
Really nice.
So, and then all I had to do was run in this directory, run mix build. It grabs everything. And it builds it. And that would have worked even if I didn't have any tech or anything else. The only thing I need installed on my system beforehand is Nix. And it will go get everything else that I need. Not only that, I can ask Nix for a shell where all those specified dependencies are present. So because I have tech as a dependency and that tech package gives me a bunch of the tech binaries, I can run PDF LaTeX, I can run LaTeX MK. But if I go outside this shell, I don't think I have PDF LaTeX. Yep, I don't have PDF LaTeX. So I can get a shell with just an ephemeral shell where I have those things available, even without needing to install them permanently on my system. So I hope that gives everyone a little bit of an idea of what Nix is, what you can do with it. Let's see. I'd like to show off copying Nix path and a closure as well. Oh, another thing that is neat. When you run Nix build, it drops a symlink, so you don't have to kind of guess or read the output to look at the store path. It drops a symlink called result. So if I look at that, that's the result. And this, if I changed anything, if I changed how stuff was built by Nix, or if I changed any of the source files used to build this, then this hash would change. So this path would remain in the Nix store, but it would write a new path with the new store. But it will drop a symlink called result into the current directory. So one thing I can do is I can see what does this depend on, and this will be kind of surprising because I said that to build it, it depends on tech. So what if I ask it, what does it depend on? It only depends on itself. There's no other dependencies. There's no dependency on tech. I didn't tell it that tech is just a build dependency. I just told it it was a dependency. So what Nix actually does is once it's built this output, it scans through the output and it greps for anything that looks like a Nix store path. And if there's something that looks like a Nix store path, it treats that as a dependency. So if I do, this is going to dump a whole bunch of stuff. But if I were to look at just the dependencies for my user profile for Nix, it has libc, GCC, because I have GCC installed to run stuff with. It has a whole bunch of libraries. It has a whole bunch of executables. You go on and on. But all of these are just runtime dependencies for stuff that I have in my Nix profile. There's no build dependencies in there. So Nix does automatic discrimination between what's just a build dependency, what it needs to build and have available when you're building something, and what needs to be kept around afterwards. And this is really nice when you're using Nix to build software, because it means you can just take your build result and copy it and be fairly certain that you're not bringing any runtime or any build time only dependencies along with it. The only time I've had that not work perfectly is in some of the cross-compiling stuff we do at Plow, where GCC, if you build GCC for a particular target, it, for some reason, was putting the runtime libraries for that target in the same Nix store path as GCC itself. So the GCC runtime libraries that we needed for our cross-compiled stuff included the whole cross-compiling GCC as a runtime dependency. And that was fixed simply by modifying the GCC derivation so that it put the runtime libraries in a separate place. But also notice that it can automatically get all of the transitive dependencies of something that you built, which means that you can also just copy all of these paths. If you want to use something, you just copy a path for something in its transitive dependency to a Nix store on another machine, and you have it available on that other machine. You just have to put a symlink in the right place. I don't have a target machine set up to sort of show off and do a Nix copy to, otherwise I would. But so I think that's all I have. Does anyone have any questions at this point?
Give people a second just to see if anyone has any. I hadn't even thought about that problem with the cross compiling and that Nix trick.
That was why when I was trying to get the binary sizes down, that was what was going on. That was why our ARM binaries were several hundreds of megs, and they suddenly dropped to between like 12 and 25 megs. Most of that was it bringing all of GCC along with it.
Yeah, that makes a lot of sense. Okay, well, I don't see any questions. I think I kind of asked the questions that I wanted to along the way.
Sure.
Thank you so much, Edward. I thought it was a really interesting talk. Nix has been a really interesting journey for Plow. Edward and a couple other people have kind of pushed us towards it, and I've been very happy with the results. I feel like our builds are much more reliable than they were. We get to use the same sort of system to do builds across multiple languages. It's just well put together. Really, a lot of the ways that you would try, if you were to sit down and try and think about this, you would probably implement something similar, only not as good. That's always a good sign for a software project.
One of the other things I'll mention, like I showed off where I just brought in the source files for the slides, and I didn't have any of the tooling installed on my system beforehand, and I just ran Nix build and it went and grabbed everything. What that's done for us at Plow is almost completely eliminated a whole step of new developer onboarding or new computer for a developer bootstrapping, because we just have to download our repository at Plow and run a script that basically just calls Nix build, and it will grab all of the build tooling, all of the exact right versions of GHC and buckle script and everything else, and build our system. And with just a little bit of extra Nix code, we actually have some extra developer tooling that you get when you go into a shell for one of our Haskell packages or one of our Reason packages, so that all the developers are working with the same tooling all the way through. And that's huge, because it eliminates a whole step of I'm having this problem and you're not. That still happens, but it eliminates a whole step of, well, are you using the same GHC that I am, or the same dependencies for GHC that I am, or the same exact version of Reason that I am? It just takes that whole it takes a whole bunch of debugging hours out of the equation as well.
Yeah, that's been a really nice benefit. And just in terms of like my use of Nix on my own, if I want to play around with TensorFlow or Torch, something, some very complicated to set up packages, that used to be something I would reach for a Docker for, and now I'll reach for Nix, which makes it a lot easier to use. Interacting through a Docker is, I think, more difficult than a Nix shell. But
and the other thing is too, someone else mentioned this to me the other day when we were talking about Nix, that the same person who made the analogy to like Nix builds sort of look like building in a Docker, but it's composable, because I can just say if I want to build something using, say, TensorFlow and some other library on top of CUDA, I can just say I want both of those there. I don't have to try to copy something from somebody's Docker file into another Docker file to get a composed system with both of them.
Yeah. somebody saying thanks for the talk, and I want to echo that too. It's really good. So I guess with that, again, if anyone else has talks, we'll always be looking for those. I'll try and get a couple more scheduled for through the year, and maybe at least 2 or 3 more. I've been reaching out to a couple people at Plow, but I would love to get some other talks from people. And other than that, I guess have a good rest of your